Hey Earthlings, this is Mrs. Vandalay bringing you some EMR notes. Sorry I can't be with you today, so you got me in a video instead. So today we're going to talk about EMR. So if you have your notes ready, let's begin. So what is EMR? EMR is electromagnetic radiation. So radiation is a form of energy that's given off by really all things, okay? Things that have heat, things that give off visible light, and you're going to find out there are other forms of energy included in EMR. So the next, hang on, go, there we go. So my next slide is, these are the different forms of the electromagnetic radiation. So what are some examples? Well, look at the picture. The radio waves. Look at all the different types of radio waves. We have AM, we have FM, TV, mobile phones have some of that microwaves idea, the radar, your microwave oven, okay? So all that stuff has a radio spectrum. All right, then we have what I would call next would be the infrared, and that you think of typically heat. Perhaps you've seen the infrared goggles in some movies and things like that. It's kind of interesting there. Look at this teeny tiny portion right here. This is a teeny tiny portion. That's visible light. So out of the entire spectrum of electromagnetic radiation, only a very small portion of it is what we can see. Ultraviolet, you probably have heard of. Those are your black lights. Those are your tanning beds. And then we have X-rays, so you think of like medical X-rays, you can see that. If you've been to an airport recently, you can see that the baggage screener has that. And then the gamma rays, those are the most energetic. And those are only from the cosmic, okay, that naturally occur. So let's go to the next slide. So now we have the insurmountable expanse, okay, and we briefly talked about this when we started our whole astronomy class. So how long does it take the spacecraft to travel our solar system? This is a spacecraft, all right, this is not the Voyager. On the moon it took 3 days. If I took that same spacecraft, it'd take from here, from Earth to Mars, 7 months. And let's get crazy, if I want to go from here to the planet Uranus, 9.5 years, okay, so that's crazy. What about closest star to the sun is the Alpha Centauri A. There's actually 3 in that cluster, so the closest one in that cluster is A. It would take us 4.3 now light years. So 1 light year, if you recall, is the time it takes for light to travel in 1 year, okay, so that takes a long time. And then it would be 78,000 years by spacecraft, and that is just crazy. So the closest galaxy to the sun is the Andromeda, and that would take us 2.5 million light years and 45 billion years by spacecraft. So again, that is just crazy, isn't it? So I don't think really it's ever going to happen that we're going to send something out to Andromeda. Okay, let's go on to the next one. This is where this measurement comes from, okay? We talked about those distances. If you recall the very last page of that first bit of notes that we did, when we did all this math on there, and we talked about all these distances, we said, so how do we know? How do we know that these distances are true? All right, well, we can look at the electromagnetic radiation spectrum that these things give off, okay? And in our history discussion, we can see how the EMR was related to temperature, to intensity, and since then they've also realized that that has something to do with how old the star is, okay? So we can use this technology to know how far things have gone, okay? So it says, despite these huge distances, we know quite a bit about the universe. It says almost all the information we have comes to us through this electromagnetic radiation. Okay, and then again, what is this electromagnetic radiation? It's any way in which energy is transmitted through space. So once again, it could be radio waves, and they use those. It could be infrared. It could be microwaves. It could be gamma rays. It could be X-rays. All right. So any way in which the energy is transmitted through space. So what kind of information can we get from EMR? All right, so what can it tell us about the stars and the galaxies and planets? Well, we can learn about the brightness. Okay, if you recall that history lesson about Annie Jump Cannon, she was looking at the brightness from the spectra. We can learn about the temperature, again, and the HR diagrams we heard about earlier compares both intensity and temperature, and those come from EMR. We can talk about mass through there. There's a relationship between energy and mass. We can talk about rotational speed, believe it or not. We can talk about movement, and that's very interesting. We're going to talk about this a little bit later on when I'm back with you in person. And then it says what they are made of and in what proportions. I don't know if you recall that lesson in history we talked about where the one woman, Carol, I remember her last name, Pruitt, I think, she was saying that the sun has like 1,000,000 times more hydrogen and helium than some of the base metals that we have here on our Earth, and her professor rejected her thesis for that. And 4 years later, he said, my goodness, you're right. So we can look at these spectrum and also determine what elements or what compounds even are in there and in what proportions. So look how much that we can tell by EMR about our stars, galaxies, and planets. It's pretty amazing, isn't it? Okay, let's go on. So, oh, here we go. Remember Annie Jump Cannon. So here's the HR diagram. This is an example of what I was talking about. So this is your absolute magnitude, okay, how intense it is, and this is the spectral type. So really the temperature. So hot but dim is over here, cool and dim's over here, cool and bright, and hot and bright. So we can classify, here's our sun, by the way, through both things, the intensity and that type, and classify the types of planets that way. Okay, so let's talk about visible light. So visible light is the only kind of electromagnetic radiation that humans can detect with their eye. And I didn't mean to point to my eye, I just had something in it. All right, so let's see, it's only a small portion of the electromagnetic radiation. And what else? Until recent history, this is all that astronomers had was their visible light. They didn't have anything else to really help us out. But today, like I said, we have the infrared photography that is really fascinating. If you look at some of the pictures of that, they have bouncing radio waves off of things. So that's just recent. But until really, it was 50, 60 years ago, all they had was the visible. And then finally, visible light does not tell us the entire story. Oh, by the way, I haven't said so. If you need to pause because I'm going too fast, you can always hit the pause button and then finish writing this stuff out. So these are the other forms of EMR. It's all listed in question number 2, examples. So again, you can see everything there. So I'm making a point with this diagram, though. You can see radio waves. Now look what you see here. What does this represent? All right, this is looking at a wavelength, believe it or not. And so we can be looking at what's the difference between all these different types of EMR. This diagram does a really nice picture with that, or shows you that really well. All right, so let's talk about waves. Okay, I was just showing you those waves. So here's different kinds of waves. So let's take a look at this. All electromagnetic radiation travels in the form of waves. All of it does. Okay. So a wave is what's kind of like a disturbance of some kind of repeating pattern. And I also put here, think of a ripple in a pond, okay? So that would be a wave. Now, are all waves the same? And the answer is no, they're not. So then we can say this is important, and this is letter C, all electromagnetic radiation moves at the exact same speed, which is 300 million meters per second. It is the fastest thing we know out there. Our Voyager can't go this fast, okay? We have yet to create anything that can go as fast as the speed of light or the speed of all electromagnetic radiation. So that's a constant, okay? So what does that mean? Well, c is the speed of light. And what we find is that there's an equation where C is equal to lambda, which is our wavelength. Lambda and wavelength go together. And then what is this V looking thing? It's actually the Greek letter nu, which is frequency. Okay, so if you put those two together, if you multiply those two together, they will always equal 300 million meters per second. And notice that the units, meters times 1/seconds, is meters per second. So it is a constant. So when I go back, give me a second here. When I go back to this, these have different wavelengths. So if they're all going at the same speed, if they have different wavelengths, well, they're going to have different frequencies too. Okay, so let's go back to this again. All right, so, oops, let me move my picture here. Maybe I'll put it up here. All right, so what do you notice here? So this is red light, and red light has a wavelength of roughly 700 nanometers. So don't worry too much about what a nano is, but it's a very small quantity, all right, 10 to the negative 9th. So that's my wavelength. Red is 700. Now, if I were to count frequency, where did I get 3.5 from? Where did that number come from? Well, watch. So this is about a half. Then I go 1, 2, 3. So I'm measuring peaks. So there is about 3.5 peaks, if you will, in this one line. So that would be 700 times 3.5 should give us, in that sense, that number of 3 times 10 to the 8th meters per second. Okay, but look down here. Look at this violet line. Okay, aren't the wavelengths a lot smaller? If I were going from distance from the top of each peak, that's a lot smaller quantity than the distance from this peak to this peak, isn't it? So notice that my wavelength went down. But look what happened to my frequency. If I were going to count my peaks, I have one peak, 2, 3, 4, 5, 6, 7. If I count all the way over, it's 15 peaks, okay, according to this picture. Now, this is just a man-made drawing. Unfortunately, if you do multiply those numbers together, you do not get that 300 million meters per second, but it's a good visual anyway. So the shorter the wavelength, the longer the frequency, and that's important, okay? That's what you need to know, okay? Let me go on here. Go on. Turn pages here. I'm not done yet. Oh, okay, sorry. So here we go. This is your II. It's actually, coming up there. So it says, meaning, as the wavelength gets bigger, this is what you need to know, frequency gets smaller. And I wrote, this is important. So make a big deal about this in your notes, all right? This is important. As the wavelength gets bigger, frequency gets smaller. Okay, so I'll let you pause that so you can write that down. Okay, so let's go to the next page. Oh, good. So let's look at letter D. All electromagnetic radiation has energy. So what does this mean? Well, real quick, Max Planck discovered this relationship between energy and frequency. So what's important? The equations is important. E, which is energy, is equal to h times nu. That's that frequency again. All right, and h is Planck's constant. So it's just a number, okay? So what now? Look what happens here. As frequency goes up, energy goes up. All right, this is just a number. So if you multiply frequency by a number, you get energy. So what happens if frequency gets bigger? Energy gets bigger. That's important. Okay, so as energy increases, look what happens to lambda. Lambda decreases. Okay, so let's go back and look at that picture one more time of our waves. Okay, well, here we go. Let me move this down here now. Oops, oops, oops. Come here. There we go. Okay, so now what? Notice my red light has the longest wavelength. So what does that mean? My frequency is low, my energy is low. But look at my violet, okay? Has a high, a low wavelength, but has a high frequency and a high energy. So which one gives off more energy is your violet versus your red. And that's at the visible light. And when I see you next time, I do have a demo that I can show you that shows this, okay? All right, next. Look at the next one. We can do it. Come on. Oh, there we go. So we're back at looking at this picture again. So you thought maybe, you had to write all this stuff down. No, I took that same picture from our second slide, and look at here. So if my infrared is over here, here's my red. Red is high. Well, as I go further towards the radio waves, they're very high. All right, radio waves have extremely high wavelength, so they have very low frequency, they have very low energy. All right, and if I go over here to gamma rays, they have extremely small wavelengths, really high frequencies, and really high energies. Those are the ones you got to be careful of. So let's think about this. Right now, radios are going all over the place. Do you have to protect yourself from radio waves? No, you don't, not at all. Okay, so it has low energy, you don't need to protect yourself. Okay, but as you go to the right in this diagram, you should. So don't we need, let's say, sunscreen for the ultraviolet light? Yes, we do. When you go to, say, the dentist's office and you get x-rays, don't they put this lead vest on you to protect you? And back in World War II and the Cold War, they were very worried about nuclear bombs, which give off gamma rays. They had bomb shelters in place with leaded walls to protect them from gamma. So yes, these have very high energy, okay, and very low wavelength. And then this is something about telescopes, okay? So what's going on here? We have different telescopes that will measure these different EMRs. So the radio telescope, look at this, more than 1 millimeter in wavelength. That's pretty big, actually, for EMR. Okay. So what about far infrared, all right? We have different type of telescopes that can measure those. They're pretty cool. What's happening to the wavelength? Well, they're getting smaller, aren't they? What about visible? Visible spectrum. These numbers are getting small. Let me move this out of the way again. All right. So what about ultraviolet? These nanometers are really small. X-rays are even smaller, and gamma rays have even smaller wavelength. Okay, and we can fine-tune our instruments to measure these different wavelengths. Okay, so that's as far as my intro goes. Please answer those 3 questions based on this chart, and I'll see you next time. Bye-bye.